So I'm going to spend some time, just the beginning, probably not very long, to use GPT and Perplexity to try to clarify more how monads work and just category theory in general. So I've been watching these videos which are extremely good from this guy here. I watched the entire playlist. The first one has 3. I'm probably gonna watch all uh, the other 2 playlists, and also this playlist here, which is very good as well. But I still don't understand very well. And before this, I don't remember exactly how I got into monads, but apparently it's something that is used on Haskell. And Haskell is a declarative programming language that is, as far as I know right now, is a language that people that are good at math use. And it seems that the monads is the main thing, like it's one of the main things from the language. Yeah, I think I remember. So I was reading from, I think, I'm not 100% sure, but I'm pretty sure that I've got to know about this from reading about some papers on compilers from this guy here, which I don't know how to say his name, Graham Houghton or whatever. It's about calculating compilers. And I think on all of these papers here, he uses Haskell to talk about it. So I think that's how I got into monads. And then I watched a lecture, the first lecture that I watched, that I kind of, it was like the simplest way that I've seen people explain is monads just a flat map. So it's a structure that has an object. So like think about a list that has strings on it. And then after you use a map, you still get a list on the results, but with a different time. So it's like a structure that has an object that changes, that implements a function to change the objects inside of the structure and maintain the structure. That makes sense. But based on the videos there, it's a very confusing thing to understand. So I'm trying to clarify now what exactly it is. And after, I'm probably gonna watch the videos again on the playlist. And yeah, spends a bunch more time trying to understand how it works. So I'm just gonna use GPT probably in the beginning to see if I can clarify some things, and then probably I'm gonna continue to study the examples on assembly x86. I also did something on SkyDraw there, but like before, I'm thinking about like I'm probably gonna watch all the other playlists because the thing is I kind of think I understand, but I'm not 100% sure if I understand how it works, because I think like the videos also don't like this first play the playlist from this guy here is very good because he puts in the context of programming, but since he uses Haskell and I don't have experience on Haskell, I'm not 100% sure if I'm understanding what he means by the stuff he's saying correctly. But this is basically the mind map that I have right now, or like the idea that I have on how it works. So I have objects, which is A, B, and C. Those objects form a set. And the way that I'm thinking about it in my mind right now is that a set is like a type in programming languages. But I'm not 100% sure, obviously, if that's how it works or not. And then from each object, you have functions so the function performs something, does some operation on the object and transforms it into another object. And then this object is going to be parts of another set. So like functions are transformations on objects that change sets. And a functor is a function, but for sets instead of objects, as far as I understand right now. And an endofunctor is a functor that transforms the set itself. So the classic way that I've seen people explain monads is that a monad is a monoid in the category of endofunctors. So the monoid, I also don't remember really well what it means exactly, but I think a monoid is just a name for the whole structure. So it's a set of objects, as far as I understand. And then the monad would be this endofunctor. The monad would be this endofunctor on the monoid. So it's a function of the set that transforms the set itself, and by changing the objects that exist inside of the set, as far as I understand. But it maintains the structure. So I'm just gonna read the stuff that I asked ChatGPT so far, and I'm probably gonna ask some questions to ChatGPT and Perplexity. And depending whether or not it's hard to find resources through like articles, I might read the articles, but probably not. I'm probably gonna go to start studying or continue to study the assembly code right after I just spent some time on this.
That it uses, primarily related to function types and monadic operations. Greater than Haskell. The greater than symbol in Haskell is used for defining the type of a function and also for lambda functions. Function type declaration. Greater than is used to indicate the type signature of a function. For example, Haskell copy code int greater than int add xy equals xy. Here, int greater than int means add is a function that takes two int arguments and returns int. Lambda expressions. The greater than symbol is also used in lambda expressions to define anonymous functions. For instance, Haskell copy code x greater than x1. This represents a function that takes an argument x and returns x1. Less than in Haskell. The less than symbol is used in monadic context, primarily in do notation. Monadic binding. Less than is used to extract a value from a monad. In a do block, you can assign the result of a monadic action to a variable. For example, Haskell copy code name equal to do line less than get line puts star line you type line. Here, get line is an IO action that reads a line from the console, and less than allows you to unwrap the result and store in line for further use. List comprehensions. Less than is also used in list comprehensions to represent elements being drawn from lists. Haskell copy code 2 x less than 1. This will double each element in the list 1, 5, producing 2, 4, 6, 8, 10. Summary. Greater than is used for function types and lambda expressions. Less than is used for monadic binding in do notation and list comprehensions.
So then I asked, what is a monads? Blah blah blah.
A monad in Haskell is a design pattern used to handle computations that involve some form of context or side effects, like handling failure, managing state, or performing I/O. Monadically structured code allows you to sequence operations in a way that wraps and unwraps values within context, ensuring consistent handling of these effects. Monad basics. In Haskell, a monad is essentially a type class with two main operations: greater than equal to bind. This operator allows you to take a value from a monadic context and pass it into another function that returns the monad. Return. This function takes a plain value and puts it into a monadic context. Monad type class. The monad type class is defined roughly like this in Haskell. Haskell copy code class monad m, where greater than ma greater than a greater than mb greater than mb return a greater than ma. Ma represents a value of type a wrapped in a monadic context m. Greater than equal to pronounced bind takes a monadic value ma, extracts its inner value, applies it to a function a greater than mb, and produces another monadic value mb. Return is a function that takes a plain value and puts it in a monadic context. Example of a monad maybe. The maybe type is a simple monad that represents computations that might fail. It has two forms. Just a represents a successful computation containing a value a. Nothing represents a failure or missing value. Haskell copy code using maybe as a monad set divide. Double greater than maybe double set divide 0 equal nothing. Return nothing for division by 0 set divide xy equal to just xy. In this example, set divide takes two double values and returns maybe double and monadic result that may be nothing or just a value. To use this value, you need to sequence computations using greater than. Handling cases where the result may be nothing. Extracting a value from a monad. In the context of Haskell, extracting a value from a monad means using greater than equal to get to the inner value while respecting the context or side effects that the monad represents. Example of using greater than equal to extract in a do block. With monads like maybe or IO, you can't directly access the contained value. You need to extract it in a controlled way. For example, Haskell copy code say compute maybe double say compute equal to x less than say divide 10 to y less than say divide x3 return xy. Here, less than in the do block allows you to extract and work with values from maybe as if they were plain values. If any of the computations result in nothing, the entire block will return nothing without needing extra checks. Intuition for monads. Monads are essentially tools for handling computations with context, like optional values, maybe IO, or side effects. Instead of removing context, monads give you safe, composable ways to work with it.
So as far as I understand, they're on the. So this is Haskell code, as far as I understand, and this is basically saying that. I think that this can be thought of in the same way that this works. So as far as understanding Haskell, you don't have classes, you only have functions. So a monad is like a way to be able to have side effects on functions, because this idea is like I kind of understand the concepts, but it's not very clear on my mind. But so as far as I understand, you have the idea of a pure function, which is just a function that you put an input, which would be the arguments, and then you get the return, which is the outputs. And across the execution of the function, it doesn't change anything on the global state of the program. So a function with side effects would be a function like that calls an API, for example, or that changes the value of a global variable. And I think that usually people try to avoid this because it makes it more complicated to figure out what each thing does. But I think that there are trade-offs like everything, so it's probably not going to be. I think just pure functional programming. The idea that I have in my mind right now is that functional programming is like a binary state machine, so it's not Turing complete. It's impossible in the real world to have programs that only have functional programming, because you need the external state, which is the memory, to make it Turing complete. So on Haskell, because of the nature of the programming language, it only allows to have pure functions, which are functions that don't have side effects. In order to bypass this, they have this structure that is called the monad. So I think what this is doing, an analogy, but obviously I'm not 100% sure because I'm just learning now, but I think it's similar to the this keyword. So basically what this is doing is declaring a function that is going to return another function that changes the type of A, I think. So A is the initial type, then it has this function which is going to return the B, which is the other type. And this is basically creates a reference to the function. So I would think about it as a function pointer, and then it's returning the transition. So it's like returning the function pointer. So assume when you call this, you would be calling the function. You would be changing the state of this thing here by implementing the function, which is MA, which would return MB.
M. In category theory, a monoid is an algebraic structure that consists of a set or object along with an associated binary operation and an identity element. Monoids are widely applicable in mathematics and computer science, and in Haskell, they are represented by the monoid type class. Formal definition of a monoid. A monoid consists of a set or object. Let's denote this as m and m. A binary operation, a function m times m right row m that combines two elements of m to produce another element of m. An identity element, an element e min m such that for any element a in m equal to a c dot a equal to a c dot e equal to a equal to a equal to a. Additionally, the binary operation must be associative, meaning ab c equal to abc for all abc and a c dot bc dot c equal to a c dot bc dot c quad text for all abc and maps equal to abc for all abc. Example: strings with concatenation. Consider the set of all strings with a binary operation of string concatenation. The identity element is the empty string because appending to any string returns the string unchanged. Associativity holds because string concatenation respects grouping. Hello world equal to hello world hello c dot world c dot equal to hello c dot world c dot hello equal to hello world. Therefore, the set of all strings with concatenation forms a monoid. Monoid in Haskell. In Haskell, the monoid type class represents this concept. It includes two main elements. Mempty represents the identity element of the monoid. Mapend or the infix operator less thank represents the associated binary operation. Here's the definition of monoid in Haskell. Haskell copy code class monoid m where mempty m append m greater than m concat m greater than m concat equal to full of m mempty. Example: list is a monoid. List in Haskell are a natural example of a monoid. Mempty, the identity element for list is the empty list. Mapend, the binary operation is list concatenation. Associativity, list concatenation is associative, meaning x s y z is equal to x s y z is. Why monoids matter? Monoids are powerful because they provide a way to combine elements consistently regardless of how they're grouped. This property is useful for accumulating results, reducing lists, and composing functions, especially in functional programming where immutable structures are essential. In the context of category theory and algebraic structures like monoids, the terms object and set have specific meanings. 1. Sets in algebraic structures. In algebraic structures, e.g. groups, monoids, and rings, a set refers to a collection of elements that follow certain rules of operations. For a monoid, the set usually represents all possible values that can participate in the binary operation. For example, in the monoid of integers under addition, the set is the collection of all integers and math uses. The binary operation is integer addition. The identity element is 0, 0, 0, 0. Since adding 0, 0, 0, 0 to any integer returns that integer. The set in this case is the carrier values for the operation. It's the domain within which the binary operation identity.
Hey, Speechify here. You've exceeded your HD word limit. In order to continue enjoying your experience with high-quality voices, please upgrade your subscription by clicking the upgrade button. If you're not ready to upgrade, you can continue listening with non-HD voices.
Are defined.
Sometimes Speechify does this. That I remember happens like the previous time that I was reading books, and I think that when you reach some limit that they have on the back end, it stops or breaks or whatever. And I'll just see if I can log in again.
Redefined.
I think it was because of the ChatGPT, probably the site.
In category theory,
Theory. Class inheritance doesn't have a direct one-to-one equivalent, but there are concepts that resemble inheritance as core ideas, particularly around functors, subcategories, and initial objects. 1. Functors is a rough analogy to inheritance. In object-oriented programming, inheritance allows one class of child to inherit properties and behaviors from another class of parent. In category theory, a functor can be seen as a mapping that transports structures from one category to another, somewhat like how inheritance brings a parent class structure into a child class. A functor FF between two categories, Control C and Control D, maps objects, Control C, objects, Control D, maps morphisms, functions between objects, Control C, and morphisms between the corresponding objects, Control D, preserving composition and identity. In programming, we might view this as similar to how inherited properties and methods are mapped from the parent class to the child class, where the child inherits or maps the structures of the parent. Example in Haskell. In Haskell, the functor type class defines a structure that can be mapped over the function FAP. For example, maybe and list types implement functor, allowing you to apply function to each element of these types in a uniform way. This way, functor serves as a template for types that can contain or structure elements, much like a base class might define methods that subclasses inherit and adapt. 2. Subcategories is a notion of subclass. A subcategory is a category formed by restricting the objects and morphisms of the larger category. This resembles a subclass that inherits only a subset of properties and methods from its superclass. For instance, if we take a category of all sets called set, we can form a subcategory of finite sets. This subcategory contains only finite sets and functions between them, inheriting the structure and operations of the larger category. In programming, this is similar to creating a subclass that inherits only the relevant parts of the superclass's structure. 3. Initial and terminal objects are special cases of inheritance. In some contexts, initial objects and terminal objects serve as generalizations of inheritance. An initial object is an object in a category with a unique morphism to every other object, while a terminal object has a unique morphism from every other object. For example, in the category of sets, the empty set is an initial object with a unique function from the empty set to any other set. A singleton set is a terminal object, as there is a unique way to map any set to a set with one element. In object-oriented terms, you can think of the initial object as a highly abstract base type, like an abstract class with no methods, while a terminal object resembles a final class with only one possible structure. 4. Inheritance and subtyping via category theory. A more formal treatment of inheritance aligns with subtyping. Subtyping can be understood as a structure-preserving relationship that fits well within category theory's notion of morphisms. For example, if a class B inherits from A, then instances of B can be seen as fitting into the category of A-like things by respecting A's properties, which aligns with category theory's emphasis on preserving structure through morphisms. Summary table. Programming concept category theory. Analog class inheritance functor. Mapping structure subclass subcategory abstract base class initial object final class terminal object subtyping morphisms. Structure preserving relationships. So while inheritance isn't a direct concept in category theory, functors, subcategories, and morphisms serve as useful parallels for thinking about structure preserving relationships, mapping, and specialization within a categorical framework.
I'm gonna ask about, because morphism is still kind of weird to me as well. And this is the part that I mean that it's kind of hard to understand, because usually when they explain in the context of category theory, so it's kind of hard to map to programming. I don't remember, and like the thing that is kind of weird is that like because they are explaining in the concepts like they're talking about for the most part on the videos that I watch they just draw this kind of circles and the arrows, and then depending on the way that you draw the arrows, there's different meanings, and that's the part that is kind of weird. So, for example, if you combine B and A, you would have a pair. So a pair is like multiplying both of them, and then you would be able to get C, for example. And then in this situation, you're gonna have another name there. I think it's home set, the name. And then you can map these pairs into from one set to the other set, and then there's that has another name as well. But it's kind of hard to understand what they mean exactly by this, because and this is the reason why I'm trying what I'm thinking about going back, because I'm not really sure. I don't remember really well if he defined what exactly does it mean to have an object. I'm just gonna ask about morphism again. But I think that there might not be a definition for the object, because it might be just this abstract thing and it's just a concept that is a generic concept that can apply to a bunch of different things. So it's more about the set would be more about the structure, and that's the reason why I'm thinking that as the sets. ChatGPT said there that the set would be the instances of all possible integers. So, but I think that makes sense to think about a set as a type, and then think about the objects inside of a set as the different instances of that type. So you can have like an infinite amount of integers, and all those different integers would be on the set of integers. Yo, thanks for the follow. Which would be the type integer. So I think for that reason it's kind of hard to understand or like to define exactly what an object is. That's perplexed as well.
In category theory, morphisms and objects are fundamental abstract concepts that generalize mathematical structures and their relationships. Here's a breakdown of each. 1. Objects. In category theory, an object is an abstract entity that doesn't necessarily contain elements like a set does. Instead, it's defined entirely by its relationships, morphisms to other objects in the category. These relationships form a network that satisfies certain rules. For example, in the category of set, objects are sets like 1, 2, 3, or ABC, but we don't focus on the elements in the sets themselves. Instead, we look at relationships between these sets, e.g., functions from one set to another. In the category of vector spaces over a field FF, objects are vector spaces like R2 math B or 2 R2 or R3 math BB or 3 without specific focus on vectors within them. Instead, relationships, morphisms between vector spaces like linear transformations are the main focus. So, objects serve as points in the structure of a category, where each category has its own kind of object based on the context, sets, spaces, groups, etc. 2. Morphisms. A morphism, also called an arrow or map, is a relationship between objects in a category that preserves the structure of those objects. In programming and mathematics, a morphism can often be thought of as a function. The morphisms in category theory are more general.
So I think that I've seen this on the videos there that they explain using graphs. So imagine you have a set that has a structure of graphs, and then you have another set that has another structure. A morphism would be a function that translates that maps out one kind of structure of graphs into the other one. So like a kind of like applying a transformation to a structure.
General and functions. Each morphism starts from one object of the domain and points to another object of the codomain, represented as FABF, a right arrow BFAB, where FF is a morphism from object AAA to object AAA B. Composes with other morphisms. If there's a morphism GBCG, B right arrow CGBC, then we can compose F and GG to get a morphism GFACG, circ F, a right arrow CGFAC. Respects identity, each object AAA has an identity morphism IDA, text theta, a right arrow IDA, that acts as a neutral element in composition, meaning IDA equals 12 text today, circ F equals 5 equals 12 equals 12 circ text today, equals to equals 12 for any morphisms FF and GG. Examples of morphisms. In the category of sets, set objects are sets, and morphisms are functions between sets. For instance, if equals to 1, 2, 3, A equals to 1, 2, 3 equals to 1, 2, 3, and equals to A equals to A equals to AB, a function FABF, a right arrow BF, AB can map each element of AAA to an element of triple B, like F1 equals F1 equals F1 equals F2 equals top 2 equals to B F2 equals top, and F3 equals F3 equals to AF3 equals to A. In the category of groups, GRP objects are groups, and morphisms are group homomorphisms, structure preserving functions between them. For example, if GG and HH are groups, a morphism FGHFG right arrow HHH would be a function that respects the group operation, meaning F on G2 equals F on G2 on C.G2 equals F on C equals F on G2 for any element on G2. In programming, objects can represent types like int, string, list int, and morphisms are functions between types. A function f int greater than string haskell is a morphism between the type int and the type string, mapping an integer value to a string value. Summary. In category theory, objects are abstract points in a category, representing entities like sets, spaces, or types defined by their relationships to each other. Morphisms are directed relationships like functions or transformations between objects that preserve the structure of those objects. They compose associatively and have identity morphisms for each object. Category theory emphasizes the relationships morphisms over the internal structure of objects, making it a flexible and powerful framework for understanding patterns across different mathematical and computational domains.
So there are two things I wanna. Maybe I should ask, what is a monoid again? What would be explanation of what is? And the other thing I wanna ask is about endofunctors. So I'm gonna ask this one first, then I'm gonna ask the difference between a function and a functor. Then I ask about the endofunctor. Because what I wanna ask is if an endofunctor is a morphism into the same stat.
A monoid is simply a set of things like numbers, strings, or shapes combined with a way to combine those things, which satisfies three simple rules. There's a combining rule. You can combine any two things in a set to get another thing in a set. For example, adding numbers or concatenating strings. It's associative. Grouping doesn't matter when combining. You get the same result whether you combine as a c dot b c dot cat or as a b c as c dot b c dot c b. There's an identity element. There's a do nothing element that when combined with anything else leaves it unchanged, like adding 0 to a number or concatenating an empty string. Example: consider numbers with addition. The set all numbers. Combining rule: adding two numbers. Associative: abc equal to a bc, abc equal to a bc, abc equal to a bc. Identity element: 0 0 0 0. Adding 0 leaves a number unchanged. So a monoid is just something where you can combine elements in a consistent, simple way with a do nothing element included.
Hmm. This part I think is kind of weird because I don't remember really well, but like it's basically saying that like the monoid would be the transformation inside of the set from one object to the others, because that's something that they talk about as well. But I'm not really sure if it's referring to the monoid as a set structure, or if it is referring to the transformation within the set. Numbers, strings or shapes combines with each one of those things. Can combine any two things in a set in this set to get another thing in this set. For example, adding numbers or concatenating strings. It's associative. Doesn't matter when combining, you get the same results.
The difference between a monoid and a set is that a monoid includes a specific way to combine its elements and requires this operation to follow certain rules, while a set is just a collection of elements without any additional structure. Here's a more detailed breakdown of the differences. 1. Sets. A set is simply a collection of distinct elements. It doesn't specify any operations or relationships between the elements. For example, the set 1 2 3 is just a collection of numbers. There is no specified way to combine elements of the set, and no requirements beyond that the elements are distinct. 2. Monoids. A monoid is a special type of set that has an additional structure, an operation, a way to combine any two elements of the set, which we usually denote by c dot. It could be addition, multiplication, concatenation, etc. Associativity. The operation is associative, meaning that x equal to a b c, c dot b c dot c equal to a c dot b c dot c f equal to a b c. Identity element. There's a do nothing element e like 0 for addition or an empty string for concatenation. So equal to a c dot e equal to e c dot a equal to a or equal to a for any element a. For example, the set of integers with addition forms a monoid. Set the integers math thesis. Operation addition. Associativity. Addition is associative. Abc equal to a bc, abc equal to a bc, f equal to a bc. Identity element 0 0 0 0. Adding 0 to any integer leaves it the same. In short, a set is just a collection of elements with no particular operation. A monoid is a set plus an associative operation and an identity element, giving it more structure.
Okay, so I think I understand what it means. I understand what it means on the like simple example, but not sure if I understand on the abstract sense. Because like the question obviously is going to be like, because you intuitively understand, for example, a set of strings, and then like you have a set of strings, and then you have an operation that defines transformations inside of the sets. That's what a monoid is. But how exactly do you define a set of strings? So the thing that is confusing me is when you have, let's say you have two different sets. What would be the difference between translating from one set to another set and from having a transformation inside of the set? Because the way that is defining is that the monoid is going to be when you have a set and then you do transformations inside of that set. But if you have a set and then you do transformations to get another set, then it's going to be a different thing than monoid. So I think I'm going to think about a way to ask this before I ask about functors and functions, because obviously related. So maybe what would be the difference between having a monoid and having a set which when transformation like it's kind of like two sides of the same coin because what is creating the boundary. So I guess what I want to understand more is like how do you define the boundary of a set? So I think that there are two levels of the same thing. So like a set in my mind is probably heuristics in the same way you have a type on a programming language, and then the what classifies the monoid would be the heuristics inside of the heuristic. So you have the original heuristic, which is what defines the boundary of the set, and then you have another heuristic, which is what defines transformations inside of the boundary of the first heuristic. And what would define the transformations between two different sets would be a transformation that reaches the limit between the first boundary. So whenever you have a transformation that crosses the limit defined by the set, which is the heuristic of what it means to be inside of the set, you would have something different than a monoid, which would be, I think, a functor.
That's a really insightful question. Let's unpack this by looking at relationships between sets, monoids, and transformations, and when they might seem similar or even equivalent. 1. Set against monoid. A set by itself is just a collection of elements without any additional structure or requirements on how its elements can or should interact. A monoid is a set with an operation like addition or concatenation that combines elements, as well as an identity element that acts neutrally under this operation. 2. Applying a transformation to a set. When you apply a transformation to a set to create another set, you're essentially mapping each element of the original set to a corresponding element in the new set. This transformation doesn't imply any specific kind of operational structure. For example, you can take a set of natural numbers 1, 2, 3, 1, 2, 3, 1, 2, 3, and apply the transformation, add 1 to each element, resulting in a new set 2, 3, 4, 2, 3, 4, 2, 3, 4. Here, the transformation creates a new set but doesn't inherently define any operation or guarantee properties like associativity or an identity element. 3. Situations where they overlap. Sometimes transformations on sets do result in structures that look like monoids. When the transformation itself is a binary operation, an operation that combines two elements to get another element in the set. For instance, if you take a set of natural numbers m and apply the transformation, adding two elements, the set m with addition now forms a monoid. Here, the transformation addition is the monoid operation, and the identity element is 0. When the operation produces closure, results stay in the set. If applying a transformation on a set repeatedly generates elements that are still in the set and doesn't create anything outside, you get closure, which is needed for a monoid. For example, taking strings and concatenating them repeatedly stays within the set of strings, forming a monoid with concatenation. 4. Subjectivity in sets and structures. You're correct that the definition of a set can be somewhat subjective and depends on how you interpret the elements and relationships you want to explore. In mathematics and programming, you can define a set abstractly, and if you choose to add structure to it, like defining an operation on its elements, you can get something more specific, such as monoid. The choice of operations is sometimes context dependent, which can make two different sets with chosen operations behave like a monoid or other algebraic structure, even if they aren't explicitly defined as such. Summary. Difference. A monoid is a set with a binary operation that's associated and has an identity. Simply applying transformation to a set doesn't automatically provide these properties. Overlap. When a transformation on a set implies an operation with closure, associativity, and an identity, it can give rise to a monoid. Subjectivity. Sets are versatile, and adding structure is often context dependent. This flexibility is what allows us to view sets through different lenses, e.g., sometimes as monoids, groups, or other algebraic structures based on the chosen operations and properties. In many cases, defining a set with a particular transformation can lead to a monoid-like structure, but whether it formally qualifies as a monoid depends on fulfilling those specific requirements.
I think so I want to clarify what exactly is a monads before I continue to watch the other videos. But I still think I'm gonna go back to watching the first playlist because it's very good. I had to watch it 2 times. Like the problem with the playlist is that the cadence is not very good for the way that I like to learn because I'm kind of ADHD. So like if I put on 4x speed, it's like he speaks too fast, so I can't understand. But if I put lower, I get too distracted because there's a lot of parts that he doesn't say like anything. So it's kind of hard for me to understand. So like the phrase that I'm trying to clarify is the phrase about the monads. So a monad is a monoid on the category of endofunctors. So now I understand what a monoid is. A monoid is going to be a set, which is a structure. So I have heuristics that define an abstract boundary, which is the relationship between things. And then when you apply a transformation that doesn't take objects outside of the heuristic, then you have a monoid. So a monoid is going to be a set that has operations inside of itself, let's say. which I think on the videos they talk about this in the context of pairs. So the transformation from C to B, for example, would be what defines the monoid. And then obviously you can map this into the other set because you can view the relationship between the two sets are as shadows of each other or images, the way that they talk about it. So if you apply the same transformation on one side on one set to the other one, you have the equivalent like image, let's say. And I think that's so this is the thing that makes it weird as well because it's kind of like a fractal thing because it's just two sides of the same coin. So like you just build more sets on top of the initial one, and that's I think that's what is making me what is making it harder for me to understand how it works. But the way that I'm gonna think about it right now is that so you have the set, then you have the operation, and the combination of these two things is a monoid. So the category I think they talk about is the same as a set. So this is something that I'm gonna ask there as well. But I think it's pretty much the same. And the endofunctor would be the transformation from a set to itself. So I think that it is like if all these definitions and the way that I'm thinking about it is correct, then I think it's clear to me now what it is. So like a monad is something where we have a structure, and then when you apply a function to that structure, to all the elements of that structure, you're going to change the nature of its objects, but you're going to maintain the heuristic that defines what the structure is. And I think that's why it makes sense to say that a monad is a flat map, because the part of flattening the map didn't understand very well, because from what I remember, when you apply a map on JavaScript, you're just going to get a copy of the original one. So it doesn't create a nested list, but I think in some situations you do have a nested list. So I think that he says there's a flat map just to make sure that it's clear that what is happening is that you are changing the nature of what's inside of the structure that defines what the set is, but you're not changing the set itself. So you still have a list at the end, but it has it is a list of a different kind of thing.
Great questions. Let's go through the concepts of transformations between sets, functors, and the distinction between functions and functors. 1. Transformations that map one set to another. When we talk about transformations that map one set to another, we're generally referring to functions. In mathematical terms, a function is a rule that assigns each element in one set of the domain to exactly one element in another set of the codomain. So a function FADF or right or BFAD takes elements from set A and maps them to elements in set BDD. Functions are the most common type of transformation in mathematics and programming. 2. What is a functor? A functor is a more abstract concept that comes from category theory. Functors operate between categories, not just sets. Categories are collections of objects, which can be sets, types, etc. Along with morphisms, functions are other structure preserving maps that connect these objects. A functor FF between two categories, C and D, maps each object in C or an object in D, maps each morphism, function or arrow in C to a morphism in a way that preserves structure. Specifically, if you have a morphism fxy of x right arrow y of xy in category C, then fx of fx right arrow of fxy is a morphism in category D. Identity morphisms and composition of morphisms are preserved. If fxy of x right arrow y of xy and gy zg, y right arrow zg yz are morphisms in C, then fgf equal to f circ f equal to f is circ equal to f. In programming, functors are often structures that can be mapped over in a way that preserves structure, like lists, trees, or even maybe types in Haskell. Example in Haskell. In Haskell, the functor type class abstracts this idea. Fmap is a function that maps a function over a functor. For instance, fmap 1, 1, 2, 3 applies 1 to each element in a list, yielding 2, 3, 4. The list structure is preserved because fmap applies the function element-wise without altering the overall structure of the list. 3. The difference between a function and a functor. Concept description function map that transforms elements in one set to elements in another set. Functora. Map between categories that transforms both objects and morphisms, preserving structure. Functors map each object in one category to an object in another category, along with morphisms. Summary. Functions transform elements from one set to another, but do not have any extra requirements to preserve structure beyond mapping individual elements. Functors are mapping between categories that transform objects and preserve the structure of morphisms, functions in the context of programming categories and composition. In a programming context, if you're working with functors as in Haskell's functor type class, you're often working with containers or types that can be mapped over while maintaining their structural integrity.
And between categories is transformable objects, preserving structure. Objects in one category object. Yeah, I think I understand. So because the thing is, like the main difference would be that you can have a function, for example, that takes this element A and transforms this to B. But I think that the functor would be like a generic version of the function where you apply the same transformation to all the objects on the set. And the function is more like a generic thing or more flexible thing because you can apply something that maps one object from one set to any other object of the set, the other set, assuming that there is a relationship between them. So I think I understand. I'm gonna see what it says. So obviously you can take what ChatGPT says, but since I watch a lot of videos, I think is quite. I'm kind of relatively confident that this is correct. The output there. And obviously I'm gonna watch the videos again, so just learning, so it
Yes,
might
that's a good way to think
be wrong, the conclusion that I have
An
so
endofunctor is a
far.
functor that maps a category to itself, preserving the structure within that category. Specifically, an endofunctor in category theory is a functor that maps both objects and morphisms from category C back into the same category C. This means it transforms each object in C into another object within C, and each morphism function or arrow between objects into another morphism within C. Importantly, it preserves the structure of the category, which includes identities and composition of morphisms. Endofunctors in the context of sets. If we apply this idea to sets, an endofunctor would be a transformation that takes each set object and each function between sets morphism and returns them as another set and function within the same overarching structure, typically without altering their essential properties. For example, in programming, especially in Haskell, the list functor, often considered an endofunctor, takes any type AAA and transforms it into a list of type AAA, which is still in the same category of types. It allows you to apply a function to each element within the list, preserving the overall list structure. Key points about endofunctors: objects stay in the same category. An endofunctor doesn't map outside of the category it operates within. If it's working on a category of types, the output types remain within that category. Morphisms are preserved. Functions between objects or types in programming are also mapped to functions within the same category, and the composition of these functions is preserved. Structure remains intact. The essential characteristics of the category, like identity, morphisms, and composition rules, are unchanged by the endofunctor. In short, an endofunctor is a transformation within a category that changes objects and morphisms while keeping them in the same universe, so to speak, and respecting the structural rules that define the category.
So after this response, I'm gonna study assembly because I'm pretty confident that this is I'm thinking about it the correct way. I'm pretty sure I'm gonna watch the playlist again, try to watch faster.
Yes, you're on the right track. But let's refine it a bit further to capture the unique role of monads. A monad is a special kind of functor that allows you not only to map over elements like fmap with a functor, but also to flatten nested structures in a consistent way while preserving the container's overall structure. Let's break it down. Functor against monad with lists. Functor. With functors, you can apply a function to each element of the structure without changing the outer structure itself. For instance, mapping 1 over 1, 2, 3 yields 2, 3, 4, keeping the structure as a list. This corresponds to using fmap, which only transforms each element individually. Monad. A monad goes a step further by adding two key operations. Return, also known as pure and bind, usually represented as greater than equal to in Haskell. When applied to lists, a monad can transform elements and flatten nested lists in a meaningful way. For example, imagine you have a list like 1, 2, 3, and you want a single level list 1, 2, 4. With the bind operation or greater than equal to in Haskell, you can apply a function to each element of the list and flatten the results automatically. So for lists, greater than equal to is similar to concat map, which applies a function and flattens any nesting. How monads preserve structure. In the context of list structure, the list structure is preserved, meaning you still get a list as a result, even if elements within the list are changed or nested lists are flattened. Consistent behavior. The monad laws associativity identity with return ensure that operations behave predictably. This lets you chain operations like mapping and flattening without breaking the underlying list structure. So to summarize, monads let you map over and flatten lists or other structures while preserving the outer container structure and ensuring consistent behavior through the monad laws. Lists as monads, lists in Haskell are a classic example of a monad, where greater than equal to bind applies a function and then flattens any nested lists. So yes, you can think of a monad as a structure that allows you to transform elements without changing the outer structure, and with the additional ability to flatten nested structures when needed.
So I'm just gonna watch, not watch. I'm gonna study the assembly examples now. And I decided to put these two ones already. I'm only gonna translate to Enki when I have all of them, but I think these two examples. So I'm thinking about getting at least one. I don't remember if I did the switch fall through. So I'm gonna do the switch fall through now. Yeah, I think it was the next one that I was gonna do. So I think it's probably a good idea to get one example of each thing. So the complex condition is good because of the situation with the ends there. That's when you have the end, it does there's two jumps, but when you have the OR, it only has one jump, I think. Because the OR, if it worked in the first one, then it already jumps. But the end, it has to jump only after it asks for both of them. So I think that's the main difference between the conditions here. So it's comparing 0 with A. So this would be the first condition, to see if A is greater than 0. I think this jumps if it isn't. So yeah, if it isn't, then it's gonna jump to this label, which just zeros the register because it's gonna return 0. And then it's gonna execute the other stuff anyway, because this is something that I didn't know last time. But on assembly, when you have jumps like this, it's not it's gonna execute anyway after the first jump. So when it jumps from this point here to this one, it just makes the EAX, which is the register that by convention they put the return values. So zeroing out the return value, and then it's gonna execute this jump anyway, even though it didn't call, because just right after this one. So the order in which you put the jumps matter. So this part is just gonna clean up it's just I always confuse which one is which, but there is a symmetrical relationship, which is prolog and eplog, but I don't remember which one is which. But at the end of the function, it just pops the base pointer and then it returns 0. So when it returns, it's going to go back to this place here. And then here is going to compare B to C. And this part, I think this is the reason why I wanted to put this, because based on the way that they are testing here, the jump is going to be the opposite of what should be happening, because that's what the exclamation mark does. So it's comparing if B is greater than 0. It's going to do this with the compare instruction. The compare is going to subtract B from 0. And if the result's negative, it's going to set the sign flag to 1. And if the result's 0, it's going to set the 0 flag to 1. And let me open jump lower again to remember. But I think that jump lower is going to jump if this SF flag is set, which is no, maybe it jumps the other way if SF is 0. I do remember it's going to jump on the opposite of what it's supposed to jump. So yeah, so if the condition is false, obviously, if the condition is true, then it doesn't jump. It doesn't go sequentially, because it's going to do the opposite. So let me pause. So it's going to be SF equals 1. So this jumps if SF equals 1. So I was right. If SF equals 1, I think the result was negative. So let me think about this again. So if the result was negative, it means that B is lower than 0. Yeah, so this situation should be when the condition is not met. So it jumps to the else statement. Yeah, so that's pretty much what is going on. Because if B is lower than 0, then it means that the inside error was true, which means that it's going to be false, the condition. But I think the main difference is that between this one and the other task is the other task, because an OR is going to jump right away, I think. So this is after the conditioner. Oh, the OR was another situation. Yeah, it was another example. I think it was, yeah, it was this one. So if with logical. So I'm gonna put this one as well. This was the one that I was thinking about. Yeah, but I'm not gonna not gonna look into this now. I'm just gonna continue. So I'm gonna put one from each one. So probably just gonna be the switch ultra. I'm gonna do both of them again to remember. So there is one thing that is kind of annoying, that is because the compiler there, like the compiler here is going to be 32 bits. So, and the other one I'm not really sure if is the x86 64 bits. So this is kind of annoying because I'm not really, it does change a lot when you have 32 from 64 because of the size of the registers. And the size of the registers is going to impact the way that they, by convention, you deal with the operations you do. I think this is more relevant to when you have multiplication and addition that takes two different registers. So ECX is going to be the one that has the parameter, and it moves that to the stack, one below the stack pointer. Then allocates 3 rows for the shadow star, I think, or maybe for local variables. I think this one is for local variables because I remember this example. I saw this example last time. So here is moving. This is based on the offsets there. So I think it does a plus 32, which means it's gonna get RSP plus 8, because here it has 24, so it's 32 minus 24, which is 8. So I think what this is doing is moving the ECX value to EAX. Yeah, which is moving 5 to EX, then it moves through this place as well, which is local variable, I think. The v64 is, I think it was for local variables. Not really sure now. RSP32. Yeah, I'm pretty sure that's what's going on. So the EAX should have 5. It's pushing 5 to because the stack pointer should be a minus 24 now, so it should be on the value of the last row there. Oh, there was also something about the previous address, I think, on this one. But I think the calculation is correct. So it's just putting at as a local variable there, I think. So at the stack pointer is gonna put 5, but I'm not really sure. It does that to compare here. Yeah. So each case is gonna do a comparison, which is gonna subtract 5 from the case, and then it's gonna jump based on the instruction. So it's using a jump if equal. I think jump if equal is like a jump if the zero flag is set, if I remember correctly. So it's not really jump if equal, it's jump if the 0 flag is set, because it compares the numbers by subtracting them. So if the result's 0, it means the numbers were the same. So this one is is easy, so I'm gonna go to the next one. I want to see what is, but I'm pretty sure I remember this one as well. The main difference is that this one is gonna have like a sequential jumps, I think. Yeah, I don't remember really well. I think that based on the cases there, it's gonna have a sequential jump. So the main difference is the first condition here is stacking the cases on the first one. So same thing, is gonna put 5 on the ECX. I think it was slightly different last time because I was looking to the other compiler as well. But here is basically the same thing. It's putting the value on EAX, then putting the value on the current stack pointer, then comparing. And it does a jump if it is equal, it jumps if it is equal to 1, and then it checks the true again. It's basically the same thing. I don't think that this is interesting enough to put there. Let me look into the other compiler. Because I think that probably the best examples to put are the examples that are kind of different in assembly, because it's gonna matter the most. Like the goal of putting this stuff on Anki is to be able to think about the assembly from the higher level perspective, let's say. So as I'm reading assembly, I want to be able to have a clear idea of what the code would look like if it was written in a higher level language. So since the examples are basically the same for the if-else statements than from the switch, I think it's not going to matter that much if I put these examples there. But maybe it is slightly different because there's a bunch of... I think that the main difference is on the local... Yeah, I think that is worth it actually, because on the other if-else examples, it doesn't have this the TV64 here, the variable. So I think that's something unique to the switch because you need more values for, because the values you put there are kind of like local variables. Yeah, so it's basically creating a copy, I think. So the TV64 is going to be a copy of A, and then uses the copy to compare. So I'm going to put the fall through example probably. I'm going to continue. I haven't seen, I think I stopped last time on this case here. I'm going to try to go faster so I can get to the other category. So pushing 5 to the stack, I think that's one of the difference between the compilers. This one pushes through the stack, the other one uses the register. And here they also have the, so I think on this one's going to be 32 bits, x86, and they use this stack prolog, I think. I think prolog is the one that comes first. So it pushes the base pointer to the stack, then it updates the value of the base pointer. I think when it pushes the base pointer, is like pushing the old address. So in the beginning there, it pushes EBP, and then it pushes the current stack pointer to the base pointer. Then it pushes 5, which moves the stack pointer 1 row. Then it calls. And so this one here would be the previous value of ESP before the push, I think. Yeah, so it's the base of the previous stack. So it saves that address on the stack. Then it pushes the current stack pointer to EBP, which changes the current base. So the old address would be 1 row below the base of the new one. Then it pushes the CX, and this is the one that I thought that it was kind of weird, but then I remember, I think I asked ChatGPT as well. And the offsets here are kind of weird, but it's because of the old address. So it has to skip the old address, and that's the reason why it uses these values here, I think. So here is getting +8 from the base, and it's pushing that to EX. And this would be this value here. And it's +8 because each row is 4, because it's 32 bits, I think. So 4 times 8 is 32, so yeah, the values are in bytes of the offsets. So 8 would be times 8, which is 64. And because it's 32 bits on each row, it means 4 bytes on each row, which means that 8 would be 2 rows. So it's EBP +8 to skip the old address. So this is putting basically the value of 5 on EAX. Then it's going to push that to -4, which is 1 row, minus the stack rows to lower addresses, so -4 is 1 row above the stack pointer, or the base pointer. So it's just basically, and that's the convention there. So for local variables, it uses lower addresses. So like the local variables are inside of the stack, the new stack frame, and the parameters are inside of the old stack frame, because the parameters are on plus addresses. So this one is basically the same thing from the other one. Also, the difference there is the conditions, let's say. So it compares 1 here, so this would be the check here, to see if the value on EAX, which is now on EBP, which is going to be 5, equals to 1. So 5 minus 1, 4. Jump if equals, so it's not going to jump, so it goes to the other condition. It's weird that it doesn't. So jump if equal should be the label here. So in the case that it is correct, so let's say A is 1, it is going to go there. So this condition is going to move. It's going to update the value of EBP to, or the value that wasn't on the stack there on the same address, to 10, because it's going to move. So how does that? So I guess that it stacks the conditions based on the order that it puts the jumps here. Because this one would be updating to 20. Yeah, so that's the difference. So this jump is gonna happen after as well, I think. Yeah, so here it compares with true and then jumps to the same address. So the difference is the way that it organizes the jump after. So in the first situation, if it is 1, because it falls true, it's going to execute here as well. And then it jumps to avoid executing the other jumps. So this one goes to the final, which cleans up the stack. So it's very easy to understand this one as well. So I think I'm going to put this one in the examples because of this relationship between the jumps. But it's becoming a lot easier for me to understand how it works. The main difference between this one is that it has the function here, has the other function call. So it pushes 5, call the function, which I think is this one. Sets up the stack. A is going to be 8 offsets. So it's going to be the same thing, I think, with the previous address because it pushes the old one. So it's basically comparing with the value of 5 with 0 and it's jumping if it's lower or equal. Lower or equal is going to be the same thing where it's either SF or ZF has to be set to 1 to jump. So if SF is a 1, that means it's lower, so it jumps. And if ZF is 1, it means it's equal, I think. Let's see. Yeah, ZF or SF equals 1. So this is gonna jump if it worked. So if so this is the else condition because obviously your condition there is a bigger than 0. So this should be the else condition, which just cleans up the value and returns the function. So if it doesn't, so because it's an end statement, it's gonna check both. And then it calls the function here. The function sets up the stack, moves 1 to EAX and returns. That's basically what the function is doing. And then it's gonna test. So this one is different. So I'm gonna put, because this test here I've seen sometimes on x64 DBG. So I'm gonna put this example. Because the test, I remember there's some situations where it's kind of confusing to understand. But basically what the task does is it performs a bitwise AND between the two operands, and then it sets flags. So it doesn't change the values, it just sets the flags. So it's like doing an AND on the two stacks. So this is basically checking to see if the value of EAX is 0. And if it is 0, then it's going to be equal, and then it's going to jump. So G is equal, ZV equals 1. So I think that's what the reason why it's confusing, because yeah, it tests. So if the value is 0, then ZF is going to be 1. I think that's the part that was confusing me. And if ZF is 1, then it means that the G is going to jump. So it's basically, if EAX is 0, it's going to jump. So this goes to the else statement as well, I think. Yeah, and if it doesn't, then it just moves 1 to EAX and jumps to the final. Just cleans the stack without zeroing. Yeah, so I think that's pretty easy to understand as well. It's becoming a lot easier to understand. And the parts that are the most confusing so far are the flags. It's gonna get very confusing on the multiplication examples as well, because I think that those are the two main parts that are very confusing, like dealing with the flags and how they impact the conditions, and then dealing with understanding the mathematical operations on the hex numbers. So how to make sense, because obviously when you do like division, for example, you're used to thinking about the float number like all together, but when you do it on assembly, it's gonna be on separate registers as far as I understand. And also the conversion between Yeah, the examples or generic examples are gonna be very hard as well, because I think that's one of the hardest parts as well, is like clarifying the relationship between the types on C++ and the what happens on assembly. Basically pushing 5 here again and calls the function. So this one is interesting because it's a loop. It's pushing ECX, so it has 5 on the stack on the offset 8, so 5 is going to be n here probably. And pushing ECX to the stack, moving 0 to the first local variable place, so that's going to be I, as it says there. So the value of I is the first local variable on the stack. Then it jumps to the label. So what is ECX? ECX should be holding the value of I actually. I don't understand why he pushes ECX. I think he pushes because of the space. So yeah, it's pushing because it's gonna use the offset -4 there. So this push here just moves the pointer, I think. So the value of I is gonna be, it's still gonna be on the stack, but it's just doing the push to get the correct offset, I think. So it's gonna jump to this label. Then it's moving the value of I. This is a pattern that I've seen on another example, which is kind of weird, and I still don't understand very well why it does this, but obviously I assume it's something to do with the compiler. It has to be something that's like a heuristic on the compiler that does this. Like it's pushing the register on the stack, and then it's pushing the value on the register again. So it feels kind of redundant. But this should have 0, which is the initial value of I. So ECX should have the initial value of I, and it's going to compare this with n, which is the condition here in the middle. N has n is the offset 8, which is the 5 here that was pushed. So it's comparing this. And it's going to jump if greater or equal. Greater or equal, I think, is unsigned, but I don't remember. Oh, so it is signed. So if SF is 0, SF is going to be set when the value is negative. I guess it sets SF when the value is equal as well. So when it's 0, it's going to be... Oh no, it's greater or equal, the condition. So yeah, it's only going to fail if the value is negative. So if SF is not set, then the value is greater or equal. So if it's greater or equal, ECX is the value of I. So if I is greater or equal to n, which is 5. So this should be false in the beginning. So it's not going to jump, I think. This jump here basically goes out the loop. So it's not going to jump on the first time. Then compares I with 5, which is the comparison inside of the loop. Where is it incrementing I? Oh, it's incrementing here. Also, it increments on the end here. That's interesting. So based on the condition here, so it's incrementing I at the end of the... So I'm going to test if I put the pre-increment there, if it's going to change. So it doesn't jump, compares. It's comparing if I equals 5. So this jump is if it is not equal. Which means that ZF should be 0 probably. But I'm not really sure. GM. ZF equals 0. So it's basically not going to jump here. No, I think it is going to jump, so it jumps if ZF equals 0. Yeah, because if the R equals ZF is going to be 1, because the subtraction is 0. So this one is the one that is going to jump, because it's different there. And this one is the one that is going to jump to the other location, which is going to increase. Yeah, it's going to increase I by 1. So it moves the value of I to EX, then increases EX, and then it moves EX to I again. So basically updating the value of the I on the stack. I think this makes sense because it's kind of like a going in and out from the register to the stack to update the value. So I do think it makes sense to do twice, but the other one's more confusing. But if the condition is correct, then it just goes out because it breaks. So what I was going to do is just change the plus plus here to see what happens. It's basically the same, I think. So it's moving I to CX, then comparing the value that was passed as a parameter, so value of n to I, and then jumping if it's greater or equal, which is the condition in the middle. And so the order there is the order of the register. So the order you see here is going to be the order you put the numbers on the comparison. So ECX is I, and that's going to impact the jump. So let me think about this again. This part is the one that's one of the parts that is confusing. It's kind of hard to memorize. So if I is, so basically this is gonna set, because I is lower, is gonna set the SF to 1, which means it's not gonna jump. Greater. It jumps if SF equals 0, so it's not gonna jump. And then because it doesn't jump, it compares with 5, compares I with 5, and then it breaks if they are not equal. So if this is not 0, then it jumps, which is going to increment. So it's basically the same thing with the post increment and pre increment. And if I remember correctly, when like a long time ago, I think that the reason why this happens is because of some compiler optimization or something. I do remember that. As someone saying that it doesn't matter the order you put the plus plus here because the compiler is going to optimize. I think the result here is the, but I'm not really sure if that's the, or if like you have to put a flag here to see. Yeah, but I think I understand how this works. I'm gonna move to, I'm gonna see on the other compiler, then I'm gonna move to the next example. So it's basically the same structure, just like the same differences in compilers. It's gonna put the value of I on the 0, then it's gonna jump to the loop, then it puts n on EX, and puts EX into, it compares EX with I. It's comparing I, so I is on the left of the condition, and then n is on the right, which is EX. Jump greater or equal, so this is not gonna jump the first time, because the ZF is not gonna be set. Yeah, ZF is gonna be 0. No, it's SF. Yeah, the jump greater or equal that's SF. So it's SF equals 1, then, so this is gonna jump. So if SF equals 1, then it doesn't jump. Yeah, I think that's, yeah, SF equals 1. So it goes here. This should be SF equals 1, which means it doesn't jump. So it's gonna jump if SF equals 0, because it's greater or equal. So since the result is negative, SF is gonna be 1, which means it doesn't jump. So this is the exit of the loop. In comparison to 5, does the same check, the nonce. And so I'm gonna move to the next example. I think I have to put at least one loop into the Anki cards at the end. But I think it's probably gonna be very similar from what I remember from previous videos that I watched. Just moving 5 to ECX. Just putting ECX on +8 from the stack to the parameter. Then subtracts is 32 because of the offsets. So it looks like it's the same. Compares here. Just comparing I with N. And it's gonna jump if Z or SF equals 0. It jumps so it doesn't jump on the beginning. Which is gonna compare 5 with I again, and then it's gonna do the loop. So this is the loop that continues the loop. This is the label that continues the loop. It's not equal because ZF is gonna be 0. GNR, ZF. Yeah. So it does this jump in the beginning. I think yeah, this one is different actually because of the but it's just because of the condition inside. So because it increments the I inside is slightly different, but it's basically the same thing. So it's pushing the value of I to EX, increments EX, then pushes EX again to I. Then it jumps to this one, which continues the loop. And it's gonna break out based on the condition, I think. Yeah. So this jump, so if ZF is 1, it means they're equal in this comparison because I is 5. Which means it's not gonna jump here and it's gonna jump here. And this one just cleans up the stack. So it adds again here to keep the symmetry and then returns, goes back, cleans the register, and then cleans the stack on the other frame. So I'm gonna go to the next one. I think that all of these are kind of like this one might be different because of the order of the conditions, but it's basically the same. Like because like I said, I think on the previous times, I think it matters more to find points of confusion when it comes to the first principles, and don't focus too much on the variance of the first principles. Because it's a lot more important to put on unconscious competence the first principles, fundamental first principles, the beginning. Then from that point, it's a lot easier to understand everything else. I think this is a pattern for everything. It's gonna be like the mean. Like the beginner and the master are the same, but the difference between them is the place that they are coming from. So it's the reason why they do the things that they do. So in order to, in the beginning, you need to learn the rules, and then when you're advanced, you learn to break the rules. And that's the best way to think about it. So x is gonna be 5, just parameter, and it moves to there. So 5 was the. So x should be. No, x is 5. It's kind of confusing because of the condition there. So x is the thing that holds the parameter, and then it's moving 5 to I, which is 0, which is on the top of the stack. This is interesting because so here is already gonna do the loop. So it moves I equals 0 in the beginning for the assignment there. Then it's moving 5 to I to compare. No, it's comparing 5 with I. Oh, which is the beginning of the comparison there. And the judge jumps. It's not very interesting, so I'm just gonna move to the next one. So I think I already got the parts that's like the most confusing parts when it comes to this is gonna be more about the other the Anki deck that I created, which is just to memorize the flags and memorize the situations where like you have different conditions, different ways to set the flags before. So that's the fundamental pattern. You're always gonna have a operation before. Just gonna set flags, and then the kinds of jumps that are gonna happen are gonna depend on which kind of flags are set between for the operation that came before. So this one is very simple as well. It's comparing A with 5. A is gonna be here, which is ECX. So jump lower are equal. So when is jump lower are equal is gonna happen? I think it's when the SF is set. Probably. So either one of them. So here it is gonna do the jump because so I think that this is when the condition is met. Oh, this is the else statement. I think this is another part that's kind of confusing, but I'm not really sure if you can train this because it depends on the context. So this is like more of a question of how does the compiler decide what kind of jump should do based on the condition. I think like based on what I've seen, probably the first jump is the else statement, I think. So let me think about this. So if SF or ZF equals 1, it means that the condition was correct. No, the condition was false because it's testing to see if A is bigger than 5. Yeah, so the first jump is the else statement, which moves 10. So I think that this is probably a common pattern as well. Like whenever you have a condition like this, the first jump that happens is probably the else situation. And then this jump is gonna jump anyway, so and this is the go to label, which moves to 20. Interesting. The other thing that is kind of weird is that there's shoe jumps here. Like this one seems redundant. So not really sure why does it do this. So I'm gonna move to the next category, I think. I'm gonna put the for loop. So now comparison. The reason why I put comparison is because I wanted to see one of the main things that I wanted to test was I think it's probably conditional comparisons as well, like CMove, but I'm not really sure because I asked ChatGPT to get the examples. It's probably not gonna be using it's just gonna be the same from if else, I think. So I'm gonna see if anything shows up on the assembly that uses conditional move or uses tests and different kinds of ways to set a flag there to do it, to jump. Yeah, doesn't matter. So it's gonna same stuff from before. So I think 8 is gonna be the first. Just gonna be the first argument here. So A is the first argument, B is the second. Yeah, so it's moving the arguments into the stack. Then moves B in EX, compares B with A. So that's the first comparison there. See if they're equal. So this jump is gonna happen if it didn't succeed. So this would be the equivalent of the else statement there, I think. And if it doesn't, it just returns. So it's gonna jump to the end probably. So maybe I'm gonna ask ChatGPT this because I don't understand why it has 2 jumps here. But I'm not really sure if ChatGPT is gonna be able to give a good answer because it lacks the context. I'm gonna ask why does the compiler Yeah, I think it's because of lack of optimizations. So I'm not using any flags. So you can put flags here on the compiler. I don't remember really what flags do what thing. But obviously I do know that there are flags that you can use to optimize the code. I think one of them is going to be O3 or something. But I think O3 is for ceiling. I don't remember really well, or GCC. But I know for sure that there are flags on MSVC to optimize the output. So I think because I'm not using any flags, it's probably in some situations it generates redundant code. There's a lack of optimizations. But I think it is correct to say that it's not going to execute the second jump. Yeah, it executes only the first one. Yeah, whatever. So this one is basically the same stuff, like just more of the same thing. So I'm not gonna do anything. I'm just gonna move to the next example. I should probably change this file to try to get examples. The hard thing is that you kind of have to predict what. Yeah, I have to change the way that I ask ChatGPT probably to get because for these kinds of things I think ChatGPT is gonna be good. So I have to ask in a way that because it has to predict what kind of output the compiler would get. So I want a C++ code that is gonna get a resulting assembly code that has conditional move instructions. But I think that this is gonna be basically the same as the other examples. So I'm just gonna probably gonna redo this category It's basically the same thing. This is gonna be the same as well, already now. It's basically the same. This one might be different because of the cast. And sign int. It seems that it's basically the same. Because I think that's when on this situation it's probably gonna like here it also doesn't make a lot of sense because I think like it would be problematic if it was the other way around, where you have an integer and then you cast through an unsigned int. Let me do this. So. Let me put -10 here. So edx has the second argument, and it's gonna be b. So it's moving b to eax and then comparing eax with a. Apparently it doesn't do anything. I think that this can be obviously problematic because of the like this is related to the category thing, I think, because the relationship between sets. So because the integer set is bigger than unsigned sets. You can have a situation where it changes the value, yeah. So I think for testing these kinds of things, it's probably better to use x64 dbg because it's gonna be the problem is gonna be on the runtime because it's gonna be undefined behavior. So because you're casting to a lower set, so if you pass a negative number, obviously if you cast it to unsigned int, it's gonna change the value of the number, which is gonna give unpredictable behavior, I think. But I'm not 100% sure. Yeah, here in the comparison is basically the same thing. Just putting the value of b on ex and then it's comparing. So here it basically compares b with a. And it's gonna jump if it's above or equal. I always forget which one is which, but I think above is for sign comparison. Above or equal. Also, it doesn't have the flags here. I'm pretty sure on the Enki cards I put the flags. But I think it's gonna be. I think it's signed above or equal. Signed comparison. Oh, it's unsigned. Also, yeah, it does the unsigned jump because of the cast, I think. So greater than is the ones that are signed. So I think it's going to be based on the ZF flag. So if A but it has to depend on the on another flag as well, because how would it test the above situation? So I think it's probably similar to this one, but the other way around. So if either ZF equals 1 or SF equals 0, probably. It's gonna jump. So let me do the other cast again. So I'm gonna switch. So it's using above or equal here. So I wanna see if we move, it's gonna do another jump. Yeah, so I think that the cast doesn't change the value of b then. It changes the comparison, but it doesn't change the value. Yeah, so now it's using jump greater or equal. Jump greater or equal. And I think that this greater or equal is the, yeah, the sign comparison. So the main difference on the cast is gonna be what kind of comparison use, what kind of jump uses. So SF equals 0. So this is gonna happen when A is lower than EAX, which is the value of B, I think. Yeah, value of B. Which is the conditioner. So I'm going to the next one. I'm going to stop here, actually. So this last example that I'm going to do, I'm going to stop streaming. From these ones, I'm probably not going to put any... Actually, this one might be... I think I'm just going to put this one because of the float. So it's the first example that has float. So floats use another register, which is XMM0 or XMM. But I'm probably going to change the other examples because I'm going to try to see if I can get examples that use conditional move instead of the normal one. So these ones, I think that they are basically the same. So I think that SS stands for sign extend. Maybe not. Scalar single precision. There's a useful thing that I found there as well. I don't remember really well. I think it was on Twitter or something. Yeah, this chart here. So floating points are represented using this register, where it represents based on the power of 2, I think. So I have the exponents and the mantissa. And then I have the sign. And the exponent has a bias, which is a value subtract the... So it's going to be this value subtracted by the bias, the final one. And the bias is because 2 represents integers. The bias is kind of confusing to understand, like why it exists, but I think it's for an optimization on the hardware. So it's a better way, an easier way, more effective way to represent both signed and unsigned values. So this formula here, basically, you take the value of x, which is how many bits, and then you subtract from the value you have here. So I think it's just basically using you subtracting by the bias to get the negative and both negative and positive values. The mantissa is going to be the value in the left of the dots, and usually it's going to be normalized, which means that you're always going to have one value on the left, I think, of the number. And the exponent is going to be how much you put the power. Yeah. So I think it's basically the same thing, just changes the register that he's using to do stuff. This one is new, but it's basically gonna be the same, I think. It's comparing the two values on the registers. As this comparison here. Jump P. So this table doesn't have the jumps for floats. So I'm gonna stop here. Next time I'm probably gonna continue to do this stuff here, translate the or review all the examples that I have on assembly. I think before I try to get the new ones for this, I'm not gonna delete the ones that I already have. I think I'm just gonna put more examples here. I'm gonna look for examples that have conditional moves. But before I do this, I'm probably gonna look into the other ones because there's a lot more examples. Yeah, so next time I'm gonna continue to do this. So see you then.